One of the most basic operators in a field called harmonic analysis is what's called the Laplacian operator. So the idea here is, let's say you have a function. Let's just say we have three variables. What you can do with this function, you've worked with functions of many variables in Calc 3. You can do things like take the gradient. So if you remember, the gradient of f is defined to be the vector consisting of the partial of f with respect to x, partial of f with respect to y, the partial of f with respect to z, and so on. So that's the gradient of f. But there's also another operator called the Laplacian operator. And what that is you can think about it as the gradient dotted with the gradient of f. And what this does is, what you're going to do is you're going to take the gradient of f, which is this thing, and you're going to take the partial of the first component with respect to x. So that's the second partial with respect to x plus the partial of the middle term with respect to y. So that's the second partial with respect to y and the second partial with respect to z. And then because you're taking the dot product, you're going to add up all of these quantities. Okay, so this is sometimes denoted for this reason. It's sometimes denoted this kind of gradient squared of f, but really it's the gradient dot, the gradient of f, or sometimes it's this upside down nabla symbol. So this is called here, this is the Laplacian of f. And this quantity is so prevalent in the study of functions and specifically harmonic analysis that this quantity comes up all the time and has a name. It was introduced, or at least popularized, by Laplace. I actually don't know who introduced it, but it was definitely popularized by Laplace. Now, we're going to study particular types of functions. And what we're going to do is we're going to talk about what are called harmonic functions. Here, our inputs, let's just say that U maps the complex plane to the reals. So the idea is that the input of U is U is going to be a function of two variables. So you can think of U as a function of two variables, say x and y. And we're thinking of the inputs as being complex numbers z, where z is x plus iy. We're doing the usual identification of the complex plane with R2. Okay, but a harmonic function is going to be one where U has continuous second partials. So U is going to have continuous, I can't spell, continuous second partial derivatives. And a function U is going to be called harmonic if its Laplacian is 0. So what that means is that in our case, we have a function of two variables. So we're going to be looking at functions where the second partial with respect to x plus the second partial with respect to y is 0. And it turns out that there's a really nice relationship between harmonic functions that have complex inputs and holomorphic functions. And we will kind of talk about that relationship and see some of the consequences in this chapter. So this is really what chapter 6 is all about. Okay, so this is the big idea in chapter 6. Now, let's just look at an example here. Just as an example, let's look at U of xy is x squared minus y squared. Okay, so here's a function that happens to be a harmonic function. It has continuous second partials. This happens to be the criteria that we need. It's the exact thing that we need so that the mixed second partials are equal, so that this assumption right here is just so that the mixed second partials are equal, which is something that we'll need when we talk about some of the results that we have. Okay, so that's why we need a continuous second partial derivatives. So this function U of xy being x squared minus y squared is harmonic. Okay, and it's actually harmonic on the entire complex plane. So it's going to be harmonic everywhere. And what we can do is we can look at these two partials, the second partial. So we're going to look at the second partial of this function with respect to x. So the first partial with respect to x is going to be 2x, and therefore the second partial will just be 2. And the first partial of this function with respect to y will be negative 2y. The second partial with respect to y will be negative 2. And indeed, when you add them up, you get 0. You get 2 plus negative 2. So this function really is harmonic. Okay, so there's an example of a harmonic function. In the next videos, we'll talk about the relationship of harmonic functions to holomorphic functions. There's a really nice correspondence there. Okay, so we'll get into some of that soon.